So, quick summary, three main things I want to get across today. The first, I'll tell you a little bit about circuit simulators we've been working on that I don't want to say they're specific to quantum chemistry, but they certainly work well for investigating variational algorithms with quantum chemistry. Many of you know about sparse linear algebra techniques, and it turns out you can do sparse wave function types of approaches in a very similar way. The technical details aren't super important. I'm happy to answer questions about that later on, but we got into this maybe a year or two ago, and we're able to build up approximate circuit simulators where we could simulate quantum chemistry types of applications at 64 to 128 qubits, even on our laptops, but especially on NERSC, which is one of the main reasons that I chose it as a topic today. And then I wanted to tell you about two different things that we've used the sparse wave function simulator to look at. One thing in quantum chemistry that we always talk about running on quantum computers is variational algorithms with unitary coupled cluster ansatz. And when I got into this, I was always very interested. How well is unitary coupled cluster going to run on quantum hardware? Is it ever going to give us advantage? Is it actually any good? And that's kind of a loaded statement just because the ansatz and optimizing it, there's all sorts of different possibilities. But the main thing that I wanted to take out of this is if we take a unitary coupled cluster ansatz and we parameterize it with a classical heuristic, which is regular coupled cluster, we can see very similar values. I'll get into this when we go on, but the only thing I want you to take out of the slide is that we get very similar values when we compare regular coupled cluster to unitary coupled cluster. And I'll tell you in what context and why that's true. But we found that very interesting. We're able to investigate that at scales like 64 to 128 qubits, where you actually want to do some quantum chemistry on quantum hardware. And then finally, I have all sorts of different use cases. You'll hear from, I think, Antonius tomorrow on doing real materials and quantum hardware, which is what we have here, and doing a lot of tests and estimates and trying to figure out how to model these things properly on hardware. But what I will say a little bit more about today is using these sort of circuit simulators to test out what we call a surrogate optimization approach on quantum hardware. And we've done some tests at up to 40 qubits on IBM hardware with this technique. And we can actually get a signal out in doing our optimizations at that scale. So these are the main messages, going from our sparse wave function simulator to testing out various ansatz for large scale systems to trying to speed up optimization on quantum hardware. And that is the summary of the talk that I will be getting into in the next few slides. And I always want to show my collaborators at least twice in my talks. And I mentioned a couple things, real materials modeling, but we've also looked at how to do molecular dynamics with these sorts of algorithms. We've developed some new algorithms with Katie using these sorts of sparse simulations. And there will be a paper, hopefully in the next month or two, where we show how adapt VQE worked at 64 to 128 qubits also. All right, let's get into it. So I've sort of laid this as the foundation for what I'm going to talk about. I'm not actually going to tell you almost any of the details how it works. I just kind of want to show you data and people can ask me questions afterwards. But I did give you a hint, and the main hint was a sparse wave function simulator actually functions very similarly to a sparse linear algebra, whatever sparse linear algebra routine you want. You don't have to store everything that's 0 or near 0. And the same thing holds when you try and do quantum chemistry simulations. You have a register with 2 to the n degrees of freedom. Normally, when you do a full wave function simulator on classical hardware, you just store every value there. And when you do a lot of chemistry applications, whether it be real time or optimizing variational circuits, it just turns out a lot of those registers are very near 0. Why not just throw them away and use it as a knob, how much you throw away, and try and extrapolate to the infinite limit. So things like that are the games we play, and we have a whole paper on this, and you can see how we validate. And well, I'm going to show you how we validate our simulations with this knob actually in the next few slides. And I've said this a little bit, but I want to emphasize it. The first applications that we really wanted to get into by developing these sparse wave function simulators is to just ask questions about variational quantum eigensolver. I don't know that variational quantum eigensolver is the future of quantum computing. It still might be phase estimation or Krylov methods, or some of the stuff that IBM's doing on split the CI sampling, or any number of other techniques. But certainly people will be playing around with V2E algorithms. In the near term, there's all sorts of different ansatz that people have been looking at and different approximations that people have been asking for chemistry systems or Hubbard model systems or biological systems. And I wanted to get at the bottom of like, are any of these algorithms or any of these ansatz going to look useful? And I wanted to get to that by doing some classical simulations. So as I mentioned before, we've been able to get to 64 qubits. Before our work came out, I think 28 qubits was the largest that anybody had really done. So our paper is about a year old. I'll say one more thing. I do work at NASA. I can't just show new data on like a 24-hour notice. So some of this stuff is a little bit older, but even that being said, even though our paper came out probably a year and a half ago, I doubt many people here have seen what a lot of these ansatz look like at 64 to 128 qubits. There's only one paper I know that's come out in the interim by Amazon team that has, they built upon our work to some extent, I'd say, that has matched us in terms of the sizes that we're looking at least for quantum chemistry. So yeah, I've said a bunch of that. And what I'd say is there's just lots that, it might be one thing just to say, we expect this or that from V2E, but to really test this out, like, was important to me because we have so many examples of algorithms on the classical side that just don't scale. Like you think it's working, you get some great results at 10 electrons or 12 electrons, but then things fall off. I illustrate that with an example down here. This is one of my favorite papers. Actually, Charles Schwartz was or is still a physics professor here at Berkeley. He had this paper in the mid-2000s that came out, and he calculated the ground state energy of the helium atom, and he was able to do it at, so he goes up to 48 digits in the abstract. He puts dot, dot, dot. If you open the paper up, you get to 53 digits of accuracy. A real page turner for, and if you try and do this for more than 2 electrons, 3 to 4 to 5, these sorts of methods, you go from 50 to roughly 3 or 4 digits of accuracy very quickly. So scaling up and understand how things scale is very important, at least to me. I don't have a ton of time. I just want to say a lot of what we did, there's precursors to this, not just from our group, but I have a bunch of our papers where we employed various approximations to try and understand how algorithms work at scale before we were doing our circuit simulators. So Katie put out a paper on doing real-time evolution or developing new algorithms based on real-time evolution. And we did some effective things there where we're able to simulate approximate real-time evolution to like 40 to 80 qubits. We've done some tests for adiabatic quantum computing and QAOA, also at between 64 to 128 qubits. And it's not all the same approximation. We use different types of sparsity approximations, but these are the sorts of games we play. And we're able to scale up and get somewhat convincing results, or in my opinion, very convincing. I'll leave it to the audience to see the results and make decisions. But also, one thing we're also quite interested in understanding is, if we're going to eventually do phase estimation, how good are the Hartree-Fock starting states in terms of overlap, which is a key criteria. And for systems up to 150 qubits, we're able to understand overlaps and what we'd expect to happen with phase estimation. So this isn't super new. Even there are other people who've played games with this before, but I think we are one of the first groups to really push it up and certainly implemented and run stuff on NERSC, for example. And if I'm wrong, feel free to come up to me afterwards and give me any references that I'm missing. So just to get to some initial data, at least for the sparse wave function simulator, the idea is everything I said and before, and I summarized some of the ideas here. We want to do as much pre-processing as we can before we start doing optimization on quantum hardware. We love to use HPC resources. We want to also maybe match where HPC and quantum computing or where quantum computing can take over after HPC resources are exhausted. And obviously, when you do optimization on quantum hardware, you've all heard of barren plateaus. And certainly when you start getting at the scales that we're talking about here, these are things we start worrying about a little bit more. I have a lot of ideas or impressions about barren plateaus. I don't know they're my biggest worry, but certainly if people want to talk about that more, we can afterwards. So, as I said, let's get into some data. Unitary coupled cluster test. This was a molecule that my collaborator Wayne Molnitz wanted me to investigate as one of our first systems. I'm not a chemist. I said yes. He's a chemist. He knows what he wants to study. So this is one of the systems. The main things to take out of this is that we're going to test this at 64 qubits. It has 14 electrons, and the Hilbert space is enormous. And if we were to do the full unitary coupled cluster ansatz, we'd be looking at optimizing 40,000 plus parameters. And I said, yes, this looks great. Let's see how this works. Let's go. So this is, since I don't have a ton of time, this I would say is one of the main slides that I just want people to understand. And this is how we understand whether our circuit simulators work, how we do our extrapolations, how we make comparisons. This is the slide that I really want people to understand when I give this talk. So there's a lot of things going on. Let me explain a few different things here. So first off, I told you I have the sparse wave function simulator, and it has a knob. And the knob just determines how sparse. And if I ramp that knob all the way up, that means I'm going to do an exact simulation. But when the knob is not all the way up, because I'm looking at 64 qubits, I can't really ramp it up to 2 to the 64. I have this value that I can set, and I can make it bigger and bigger and make my simulations more and more accurate. So ignore the second value here. That's what the first value is. 1,000, 5,000, 10,000, 20,000. Those are roughly the number of degrees of freedom I'm retaining in my approximate simulator. I have some flat lines here. For those of you in chemistry, you know what those mean. For those of you who are not, those are various chemistry algorithms that give approximate energies for this, for any system that we put it through. In this case, running it at a truncated 64 qubit calculation. What I'll say to you is there's sort of an order of accuracy here. MP2 is the least accurate. Couple cluster singles and doubles a little bit more accurate. Couple cluster singles and doubles with perturbative triples is considered a gold standard in chemistry for these sorts of systems. And you should take that as roughly the exact energy. It might be off by 1 to 5 millihartree, but on the scale of this plot, it doesn't matter. You should take that as the exact benchmark. So what do we have going on here? On the x-axis, it's labeled number of doubles. So I told you there are 40,000 degrees of freedom in the ansatz. There's 2 to 64 in the wave function, so ignore that for a second. But the ansatz, the circuit I'm putting down, the circuit I'm testing, the UCCSD circuit goes all the way up to 40,000 if we were to do the entire ansatz. And this is a running average of including more and more important degrees of freedom from that. We have some classical heuristics in which we can rank which doubles are important, and we put them in that order. And that is what the x-axis is. So again, it is how deep the ansatz is as we go from left to the right. Circuit is getting deeper and deeper and deeper. The circuit is getting more and more accurate. The circuit is having more and more variation parameters that I'm optimizing. Okay, so the y-axis is the energy. These energies are all variational, which is to say the lower, the better. And as I said, you should take this purple line as the exact energy. And the main thing I want you to take out of this to understand how we're analyzing molecules and how we're analyzing the approximations we're making in our circuit simulator. I've sort of highlighted in 2 boxes. In the box on the left, or right for you guys, no, it is your left, sorry. The box on the left, you can see all the lines more or less lie on top of each other. That is to say, The wave function is not so complicated that every approximation that I'm making from my circuit simulator is different. They're all the same, which is to say the approximation is good enough. If I were to ramp this way down, you'd see something drift off for sure. But at least these values, they're all more or less lying on top of each other. And it's on the right, you can see where they start diverging, which is to say the approximation we're making here with only 1,000 degrees of freedom isn't quite enough to capture the complexity of the circuit, but at least these other values are able to do that. So in this sense, we're able to make these sorts of plots with increasing amount of computational power as we ramp these values up and have some understanding of how good or how far away or whether we think our results are good enough. We can do extrapolations, things look pretty smooth. That's not always true, but for a lot of the systems we're looking at, it is. So we can do a lot with this sort of technique, and having a knob in which we can make things better and better and better really allows us to smoothly interpolate and try and figure out where things go as you go to the infinite limit, both in terms of number of doubles and the number or the back end, the approximate simulator that we have. In the interest of time, I will just say one or two things here. So we were interested in understanding or giving you people a feel for why this works. And what we do is we calculate effectively an entropy for the coefficients of the wave functions we're coming out. So we do our approximate circuit simulator, we run our circuit, we get a final wave function, and that final wave function has a bunch of coefficients in it. And we can calculate the entropy over those coefficients. But not only can we do that at the end, we can do that as we actually are applying the circuit. And what you see is the entropy, which isn't an entanglement entropy. A lot of people do DMRG here, or at least in the physics community. And entanglement entropy is some idea of complexity for a tensor network state. Here, this is what the entropy, we have a similar thing going on, but for more of a configuration interaction or an exact diagonalization state. And what you can see, at least with these unitary coupled cluster ansatz, this is one example, but a lot of our UCC ansatz look like this. The wave function, the entropy is going up very monotonically over time. And that is to say the complexity of the wave function is going up pretty monotonically over time. And it's going to saturate on some value that's related to effectively the entropy of the entire wave function or the ground state wave function that you want to have. And we find this, to say that there's sort of this nice classical range of simulability. Like if this entropy goes up and up and up, we might not be able to do that full simulation, but we might be able to truncate our UCC ansatz at some value and do do some amount of approximate simulation. The other thing I want to say is when you do an approximation like what we're doing here for a circuit simulator, not the number of qubits that really determine how complex the simulation is. It's really the wave function that you're trying to get at. This red line here is at some entropy value that corresponds to the full ground state wave function that we want. And we're never going to go above that as we apply. Well, there are some ansatz that can go above these sorts of things, but in general, if you have this monotonic behavior with the ansatz that you're looking at, UCC in this case, you very nicely below that until you get all the way to the end of your ansatz where you're trying to get to the ground state. So it's not a complexity in the number of qubits, it's a complexity in the state that you want to look at. If your state is very complex, then our circuit simulator needs more and more CPU time in order to run. If your state is tons of qubits, but not very complex, then this type of approximation, this type of simulation would be very good for going into that sort of thing. All right, so I have 5 minutes left, is that right? Okay. I just want to say a few more quick things. So we did, as I mentioned in the previous part, we did a sparse simulator that's really kind of like a configuration interaction, exact diagonalization type of approximation. With various people, I've also, including Antonius, who'll give a talk tomorrow, we've also looked at tensor network versions of this. I'm not saying there's like one version that's better than the other, and certainly there are more approximations that beyond tensor networks in the sparse simulator that we're looking at, but we're starting to play around and test these things. With tensor networks, we're doing very similar tests on the Hubbard model. And without going into too much details, because I think Antonius might get into it a bit more tomorrow, we wanted to start testing various ansatz, such as the MP ansatz and EP ansatz. These are two different ansatz that people have really pushed forward as these are the ones you should be optimizing for the Hubbard model. We wanted to start testing how good these ansatz really are as we do 2D types of systems, 2x2, 2x3, 3x3, but also 1D chains. And I won't really get into the details now since I'm running out of time, but what I'd say is these sorts of ansatz, they look like they have scaling issues, but there's lots of things to say about that. And Antonius might say some more about that tomorrow. But we've looked at it in a lot of different regimes and weakly correlated to strongly correlated regimes. And the accuracy is just all over the place. And what I'd say is there are other ansatz out there like adapt level ansatz that might be significantly better, but we still need to test them and that these are different directions we're going to. And finally, in the last minute, I'm gonna skip that. I did want to say one thing about accelerating VQEs by using an approximate circuit simulator. So we did the circuit simulator stuff. We started investigating ansatz and understanding what ansatz are really worth doing. But can we use an approximate circuit simulator to speed up, say, a variational algorithm was one of the last things or more recent things that we've started getting into. We put out this paper earlier this year about surrogate optimization of various variational quantum circuits. And I just want to describe our flow very quickly before we call it a day. So you could imagine if I'm doing my approximate circuit simulator that I will get an approximate landscape that I'm optimizing over, which is represented up here. And it might be very similar if I ramp up that parameter enough, or at least push my HPC NERSC count as much as I can to the actual quantum computing potential energy surface. Now, when I go and optimize with my HPC resources, I'll get my gradients will go to 0. I'll get some set of parameters. But I'll also, if I want, I could calculate some extra quantities, such as the Hessian or things like that, to see if I can use that information when I put it on a quantum computer and actually try and improve my result more. So the idea is do as much as I can approximately on the classical hardware, and then use, in this case, the Hessian information to generate various line searches of parameters that I can run on quantum hardware and possibly accelerate the optimization. You can read more details in the paper, but we're just really getting started, in my opinion, exploring ideas in this direction. We did a bunch of test systems. I won't go too much into it, but I'm happy to take questions after, or you can read in the paper. We actually ran this on IBM's hardware up to 40 qubits. And these yellow dots are where we'd expect things if we didn't have noise. So there's a lot of things I can say about what noise is doing and how it affects us. But one of the main things I want you to take out, this is our optimization at 40 qubits for an Heisenberg type model. And you can see we're getting a signal out and the energy is going down as the iterations are going. There's still a gap between what we expect and what we're getting. And there's, as I said, we can talk about that offline. But the fact that we're getting a signal out enough that we can start doing optimization, all our collaborators think this is pretty cool. And we're sort of interested in pushing, or we're definitely interested in pushing this forward and seeing how much we can save in terms of optimization. So again, the number of shots is still actually quite large, but it is, in our initial test, this is maybe a factor of 5. Some of the systems we're looking at more effective than some of the various VQE variants that we've been testing in the past. So I'll leave it there. Hopefully I didn't go over time. What you heard today was about approximate circuit simulators. I skipped this, but testing various ansatz with the UCC over a lot of different systems is something we did, and we have a whole paper on that. And then a paper about how we can use approximate circuit simulators to speed up the variational quantum eigensolver. And as I said, I think we're just getting started there, and there's lots of techniques that we want to explore. These are various collaborators that have worked with me on these papers and different topics, and thank you for listening.
time for some questions.
Yes.
Yeah, very nice talk. So have you, for the problems where you spoke about truncation, right? Like when, I guess when the problem size becomes large enough, you will have to do some kind of truncation so that you can do this approximate simulation, right? So for those problems, have you actually tried the second part where once you found your initial state, you actually ran the second part on a quantum device?
Yeah, I mean, that was effectively the data that it went really quickly through.
Uh-huh.
But it wasn't, again, the things we've been testing are largely in the quantum chemistry realm.
Yeah.
Our first tests in IBM hardware were more like Heisenberg models, so things that are a little bit similar, but there's still a gap between where hardware is right now and being able to test like full scale quantum chemistry models, but we're interested in pushing on that. But we have tested for at least the Heisenberg-like models, is where we've done some of that, yes.
Okay, so and just quick follow-up. So do you see that the more you truncate, so I'm wondering, let's say you're running a 100 qubit problem or something where you need to, I guess, truncate a lot so that you can simulate it. First of all, is that a fair assumption that you need to significantly?
There's various realms in which this goes from completely worthless to super useful.
Sure.
I think that's, so if you can't ramp, if you have the hardest problem in the world, you probably can't ramp that knob up enough on current HPC resources where you can have help. But where I really like this is I'm trying to bridge the gap between where HPC resources are and where a quantum computer can pick things up. So maybe in the future, this won't be useful, but I feel like in the near term, we're trying to bridge that gap and we can tune those parameters up enough, I hope, and we'll hopefully do some tests in the near future where we will be able to go from the best HPC we can do to getting even 1 or 2 iterations on quantum hardware to improve upon that.
Thank you.
I think I have a quick look at so did verification hardware, but no algorithm, there are feedback loop.
Yeah. So right now, we're considering ideas in which you can update the Hessian, but right now there's no feedback loop and it's still, yeah. The first papers that came out this on the classical side was like a year or 2 ago. And they also just did not update the Hessian, but they ran a few iterations and those search directions still turned out to be good to do a couple iterations. But if you can update the Hessian and do it efficiently, that would be ideal. There is a paper too at the Virginia Tech Group where they've started going in that direction. But I have to, that's something we're considering whether we can adapt that to update our Hessian information. Yes.
Initially, will your simulator work well on a specific circuits, or you have to run it and look at that graph and then know were you good or not?
So there's definitely failure cases, and I have some pretty good ideas of when and where those are. A lot of the algorithms I'm interested in quantum chemistry are DAPS-like circuits for UCC. Almost all the UCC or UCC variants work very well with the sparse waveform simulator. And for more hardware efficient ansatz, we're doing more of the tensor network version. So, we're building a couple tools that span different regions. There's still like, if you give me the hardest problem in the world and the hardest, and the entanglement entropy ramps up very quickly, there's a good chance that none of these will work. But for the near term, you should think, or at least the way I view it is, I'm trying to tackle problems that are beyond or slightly beyond what I can do classically. And those sorts of ansatz are probably very amenable to the techniques, but you could probably invent an ansatz that we just completely fail on. A lot of the ones that people have proposed are not in that regime.
You long down from Brooklyn.